So today I'm going to be talking about finding the bifurcation values and interpreting the phase lines that go with them, and I'm going to be using some of the examples from the WeBWork homework. So we're going to start out and we're going to use the differential equation dy over dt is equal to y squared plus k. And in order to find the bifurcation value, we're going to have to set y squared plus k equal to 0 and solve for k. And when we do that, we find that y is equal to the square root of any negative k numbers. And obviously if k were to be positive, then we would get an imaginary solution because you can't take the square root of a negative number. But that doesn't happen if k is negative, because a negative and a negative will turn the number into a positive. So that's what we have there. When we move down here, this right here, these phase lines, is what we're trying to find. As you can see, this y-axis here being 0 and the x-axis being dt, we see that all of the points on the phase lines are less than 0 on the y-axis. If you can tell, they're not exactly touching the axis there. So this is what we're going to be looking for, a solution curve that looks kind of like a sideways parabola, less than y. And in order to find the bifurcation points, we're going to be trying to find all values where k returns us with one single value instead of two, as we see on the lines up here. We're going to be looking, what is this point right here where there is only one point on the phase line. And to do that, we simply just look at numbers. We just plug in numbers for k. In this situation here, if we were to plug in anything less than 0, we'll get two values. So anything less than 0 will not return to us a bifurcation point. If we plug in 0, though, for k, we can take the square root of 0, both positive and negative, it equals 0. So therefore 0 would be our bifurcation value for this equation, y squared plus k is equal to dy dt. So then we get these three diagrams here. The first one shows us that we have one single bifurcation point. So this represents k equal to 0 in this situation, where we have we have two. This represents k less than 0, because anything less than 0 for k will return 2. And here we don't see any points. We don't see any bifurcation points. So this represents k greater than 0. And we know that for all k greater than 0, we have imaginary numbers which do not give us any points on a phase line. And I have that summarized right here. So now we're going to try a second example, and this time we're going to be using dy dx is equal to y squared plus 4y plus k. And again, we'll be setting that equal to 0 and trying to factor to find roots. However, we can't do that because we don't have a k value. It's changing. So what we need to do is we need to use the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And for the c value, that's what k will be, and we'll change k for each instance. We'll use 0, then 1, then 2, and so on until we get one bifurcation point at the end. So let's try it where k is equal to 0, which is equal to c. So we have that written out here, -4 plus or minus the square root of 4 squared minus 4 times 1 times 0 all over 2. And that returns x equals 0 when when we use the positive side of the quadratic formula, and it returns x equals -4 when we use the negative side of the quadratic formula. So we have two values, and that means we do not yet have our bifurcation point. So we're going to try x is equal to 1, and here we get x is equal to -3.73 for the positive, and for the negative part of the quadratic formula we get x equals -0.26. Again, we have 2 points, so we can't conclude anything. Let's jump all the way up to x is equal to 5, and we'll see what happens there, just to see if maybe we're over the bifurcation value. And what actually happens there is that when you plug in 5 for c, we end up having a negative underneath the radical, and that happens on both sides, and that means that both the plus and the negative side are undefined. So we know that 5 has no bifurcation values, and we've gone too far. We have too many. So, because of that, we know that the bifurcation value is between 2 and 5. So let's try 3. 3 yields -1 and -3. Again, we have 2. We try 2, or we try for 4 rather, and we get x equals -2 and x equals -2, the same value. So we have our bifurcation value is 4. So down here we have graph number 1 showing that the phase line shows that the bifurcation values are too high, or too low, because we have 2 points. Phase line 2 shows that k is larger than the bifurcation value, and phase 3, because here we only have the 1 point in the middle, representing 4 in this case, that the bifurcation value is equal to k, as we see over here. I hope that helped you guys. I had some trouble with that during the homeworks, but this makes a lot more sense now. I hope you guys can benefit from this as well.